Hi, this is Dr. David Branham. Today, I'm going to talk about post-facto design and experimental design. This is very important in your forthcoming assignments and your tests. Hopefully, after this video, you will have a better understanding of experimental design, post-facto design, their advantages and disadvantages, because in future assignments, you'll be able to apply this if you're able to understand this better. So I'll start by sharing my screen and going to my PowerPoint on this subject. Okay, so today's presentation, as I said, is on hypothesis testing using experimental design and post-facto design. Hypothesis testing, all statistical tests begin with an alternative hypothesis or a premise that something will affect something else. Okay, and then you hypothesize that there will be a difference whether or not the effect, the group affected versus the group not affected. Okay, so this is basically how statistical tests work, especially in experimental design. These hypotheses can predict positive or negative effects. So you can say that an independent variable will have a positive effect on something or a negative effect on something. And what you'll be looking for in your data is this positive correlation or negative correlation, depending on what your hypothesis is. And then you will test to see if the data shows support for your alternative hypothesis. Okay, sorry, wrong direction. Okay, statistical designs. There are two basic statistical designs that can be used to do a statistical analysis. The first that we're going to cover is experimental design, and the second is post-facto design. Now, experimental design is superior to post-facto design in determining causation. What happens with causation is we want to be able to say that this variable caused an effect on this variable. It's very difficult to do. Experimental design is superior in doing that. It is a design that specifically looks for a way to show that an independent variable has an impact on a dependent variable. So it's superior to post-facto design in determining causation. However, experimental design is much more difficult to perform than post-facto design because there's many restrictions that are inherent in the technique of experimental design. So we'll talk a little bit about what experimental design does and what impact it will have on our ability to say causation has occurred and to justify our conclusions. First, three things are needed to establish causation. One is covariance. If the hypothesis says that a rise in an independent variable will result in a rise in a dependent variable, then there should be a positive correlation between the independent variable and the dependent variable. This seems pretty self-explanatory, easy to comprehend. So if we believe that, for instance, cigarette smoking causes your life to be shorter, we would expect that those people who smoke more will have shorter lives. That's a correlation. It's a negative correlation in that the more you smoke, the fewer years you will live. But we would expect to see that correlation if covariance is occurring. So that's the number one thing you need in causation. If you don't have covariance in your data, it's impossible to establish causation. You have to have that. The second one is temporal sequence. The independent variable is administered and reaction to the dependent variable is recorded. If things are done simultaneously, like you take a snapshot where one changes the other, then the sequence isn't, one changes and the other one changes at the same time. The sequence is not really established because you can't tell which variable is causing the other or whether a third variable is causing both, okay? So temporal sequence is needed to establish causation. The third thing that you need to establish causation is elimination of confounding influences. There are ways to do this in experimental design where these outside influences cannot come in and impact your results. In post-facto design, we can also do that, but it's much more difficult. Experimental design has all of these that we have listed here. It has covariance, it has temporal sequence, and it has elimination of confounding influences. So covariance, where the independent variable moves, the dependent variable moves in response. Temporal sequence, where first the independent variable moves and then the dependent variable moves in response. And then elimination of confounding influences, where we know that nothing else from the outside is having an impact on this. Now, experimental design has a lot of requirements. It's very difficult. First, you have to have an independent variable that you can manipulate. That is not an easy thing to do in social sciences and nonprofit management, in sociology, political science, government, public administration. It's hard to find an analysis where you have an independent variable that you can manipulate. That means you can make it do whatever you want. Now, there are a lot of independent variables that you can manipulate that you can't ethically use. For instance, when I used the example of cigarette smoking in the previous slide, in experimental design, you can manipulate cigarette smoking. You can force a person to smoke, and you can force a person not to smoke. That would be a manipulation, but they would have to do exactly what you wanted. You would say, you have to smoke, or you have to not smoke. And so that's the manipulation you would have to conduct a true experimental design. Obviously, ethically, you cannot do that. You can't force someone to smoke. That would be unethical for you to do that. So having an independent variable that you can manipulate isn't necessarily enough. You need to have one that you can manipulate and ethically apply to people who are doing the experiment. You must also do random assignment of your tested groups. So in a typical experimental design, you're going to have two groups. The first group will be a group that you will give the independent variable to. The second group will be a control group where they're not going to receive the independent variable. Those two groups will be compared to see if there's a difference once the independent variable is given to the experimental group and not given to the control group. You can measure to see if that difference occurs. So in order to do that, first though, you have to randomly assign people in your experiment to each group. And it's best that they don't know which group that they're in, because that will have an effect also. So there are ways to randomly assign people, but it's important that everyone has an equal chance to be in each group. If you don't have that, then you don't have a random assignment and your experimental design is completely flawed. So when random assignment is done, you can assume, if it's done correctly, where everybody has an equal chance to be in each group, you can assume that each group is perfectly equal, because no one gets to choose which group they're in. Not the researcher, not the people in the experiment, no one. You have to randomly assign everybody to a group. Now there's ways to do this. For instance, you can have a deck of cards, and then you can give each person a card and say, okay, this group is in the control group and this group is the experimental group. And you have no control over which card they get. They have no control over which card they get. There are other ways to do it, but you have to have random assignment where each group everybody has an equal chance of being in each group. And when you do that, you can assume that each of those groups are equal. You can assume that. It's important for you to understand that going forward. Random assignment allows you to assume that both groups are equal. When a random assignment is done, you can assume that each group is perfectly equal. When the groups are larger, the assumption is stronger and the differences between the groups have more statistical power. It's much better to do a statistical analysis with a large group of subjects than with a small group of subjects. A small group of subjects makes it very difficult, even if you have random assignment, assuming that those two groups are equal is much more difficult because they're small. You might randomly get a very lopsided pair of groups. If you have a large number and you randomly assign the large number to two different groups, chances are they are equal. Each group is equal to each other, okay? In two group analysis, like I'm talking about right now, the experimental group is given the independent variable. The control group is denied the independent variable. It's often very important not to let those in the experiment know which group they're in because it will have an effect. For instance, if you're doing an independent variable where you're giving a medication to the experimental group and not to the control group. If you know that you're not getting the medication, you may feel sicker as a result. And if you know you are getting the medication, you may feel better as a result, just psychologically. That's not going to be the effect you're looking for. You're looking for the effect of the pill. So it's better not to know which group you're in so you won't have this impact. Now, these things are optional experimental design, and they make the experimental design more valid. Okay, first is matching. This is done by pairing people before random assignment is done. And then once you pair people according to selected variables, like if you have two old people in the group, two people that are 80 years old, you pair them, okay? And then one is randomly assigned to one group and one is randomly assigned to the other group. We don't know which group they're going to be in, but they're paired. And that means you know that you have two 80-year-olds in your group. The same with gender. You can pair two women and pair people of equal incomes and put them in separate groups. You don't know which groups they're going to be in. You don't know if they're going to be in the control group or the experimental group. That will be randomly assigned, but you know that one will be in one and one will be in the other. Then you'll have two groups that look a whole lot alike. And if you use matching, it's easier to assume that your groups are equal, especially if you have a small number. If you have a small number of participants, matching is always a good idea because it makes it where your two groups are more equal. So remember that you can do the pairing, but then the random assignment is the last thing you do. You can't randomly assign and then pair. You have to pair first, match first, and then do random assignment. And that helps you have equal groups. Equal groups is what you want to have if you really want to find out if your independent variable is really having an impact on your dependent variable. The second thing is a placebo. That's when in a control group, you're giving something that looks like the independent variable, so you don't know which group you're in. Remember the previous example, I said a drug may be used to see if that drug was effective in treating disease. In a placebo experimental design, each person, no matter which group they're in, will be given a pill. It's just that they won't know which pill they're getting. The control group will be getting a sugar pill, a pill that has no impact. The experimental group will be getting the real drug. No one will know with a placebo which drug they're actually getting. So psychological effects like, oh, I'm feeling bad because I didn't get the drug, or I'm feeling good because I got the drug, those go away because everyone is getting something. So there's equality on both sides with that placebo. If you can use a placebo, it's always a good idea to do it. The third thing you can do is a double blind study, where not only do the participants not know which group they're in, the researcher doesn't not know which group the participants are in either. This is a good idea because researchers want a result. It's a lot easier to publish a real result if your alternative hypothesis has evidence. It's easier to publish. So a lot of times a researcher will try to push the experimental group in a certain direction and the control group in another direction. It may be subconsciously. So you want to be able to avoid this at all costs. So the way to do it is double blinded, where the researcher does not know who is in the control group and who is in the experimental group, as is also the case for those participating in the study. Okay, an experimental design model. You can see the experimental design model here. The two-group model, which I was talking about before. Here you have a group A and a group B. Then you have the DV at the top, which is a T and a P. And then the next step is R, and then the next step is X. Okay, so in these experimental design models, A is the randomly assigned experimental group. So A will be the experimental group, B will be the control group. So the A group will get the independent variable, the B group will not get the independent variable. T stands for treatment. Treatment is the actual IV. In my previous example of a drug, the treatment would be the drug itself. In this stage, the second stage of the experimental design, with two random groups, the T will go to the experimental group. That will be the treatment, the pill. The P stands for placebo, which is optional, but a good idea in a lot of cases, where you would give them a pill also, but the pill would be nothing. And so no one would know which group they're in, but each would receive a treatment. And so the psychological effects will go away. So R stands for the reaction to the independent variable. You will, after you give the treatment, you will need to give a reaction or get a reaction. And that's will be something that you code. You measure that. And then in the end, you have a new result for the dependent variable, which may be sickness. Okay. So group A, which is the randomly assigned experimental group, if your pill works, they will be less sick. Then group B, which is the control group, in X. So that's the typical experimental design. It's important for you to know every step of this while you're doing experimental designs in your assignments and while you're taking the test. So you'll know which step is coded in the experimental design. Once completed, the mean of X in group A is compared to the mean of X in group B. A T-score is computed, and then the hypothesis results are reported. As we said in a previous video, that would mean either you will reject the null hypothesis or fail to reject the null hypothesis. Those are the only two results you can get with a t-test. Experimental design assumptions and flaws. First, in experimental design, all persons in the group will have the same reaction to the independent variable. That's the assumption. Everybody will have the same reaction. Often people from different populations will have a reaction different from the people in other populations. That happens all the time. And so that will mean that one group of people will have a really good effect, another group of people will have less of an effect, or maybe even no effect at all. Experimental design assumes everybody will have the same impact. It's a linear process. It basically says this person gets it, this person will get well. And the assumption is that everybody will react the same. Okay. The experiment will have external validity. That's another assumption that is a flaw. Okay. These assumptions that what happens in the lab will be the same thing that happens in society are pretty bad assumptions. In a lot of cases, people act much differently in a lab situation than they do when they're out in the population. So it's important to understand that external validity is constantly a problem in experimental design. We control the environment in experimental design. We make sure that no outside variables come in and affect our results. Well, when you have that controlled environment, it doesn't match up well in a lot of cases with what actually happens in the real world. People act differently in a lab than they do in the real world. We know this is the case. So that being the case, it's always important when you're doing experimental design to understand these flaws. Okay, the first one, you may, don't assume that the different populations will react the same when you get your results. It may water down your results when you make this assumption that everyone's the same, to the point where you don't get statistical significance when you should. Don't make that assumption. And don't make the assumption that everybody will act the same on the outside as they did inside the lab. Now we go to ex post facto design, which includes ordinary least squares regression. Now regression has flaws. Post facto design has flaws also. The reason why is on a couple of things. First, we do have covariance in post facto design. What we do is we look and see if the independent variable moves the dependent variable. We have that. But things that we don't have, one is temporal sequence. It's very difficult in the real world settings. These are real world settings examples where we don't do post facto design in the lab. We do post facto design in the real world and we collect data there. Temporal sequence is difficult because we usually cannot manipulate our independent variable. For instance, how do you study smoking if you're not able to do it in an experimental design lab if you're not able to force people to smoke or force people not to smoke? How do you do that? How do you do the experiment? Well, what you do is you go out in society and look what happens to people who smoke. So the sequence in that situation is pretty much there. You watch people who smoke and then you see what the impact is. But a lot of times the sequence is difficult. A lot of times, for instance, we use survey data and we ask people a question to see if their stance or their position in one area has an impact on another area. When that's the case, we don't have that temporal sequence and we have to make an assumption of causation. A lot of times that assumption is easy to do. It's justified. It's easy to assume that smoking causes cancer instead of cancer causing smoking. But in other cases in the social world, that isn't the case. So temporal sequence is difficult. It's hard in post facto design. Elimination of confounding influences is not done through random assignment as it is in experimental design. That's something that experimental design has a very big advantage in. When you have random assignment of two groups, you can assume those groups are equal. And that means those confounding influences are not part of the assignment. They're controlled for. Well, when you go to post facto design, where you go out into society, collect data, a lot of times from surveys, those confounding influences have to be accounted for in a different way. And in most cases, what you have to do is you have to collect data on those variables. So if you're doing a study and you're trying to find the effect of smoking on life expectancy, you're going to have to collect data on other variables besides just smoking. You're going to have to find out where they live, what they eat, other factors, how much education they have, how much TV they watch, how much exercise they have. If you don't control for these factors and collect that data, then people will come in and say, look, it's not the cigarettes that are doing it, it's this thing that you didn't collect. So confounding influences are a lot harder to control for in post facto design. In regression, we are able to do that by entering those variables, but we have to hypothesize what those variables are that may be confounding influences, put them into the regression model to control for them, and then see if the alternative hypothesis independent variable is actually having the impact that we expect. So post facto design has flaws that experimental design does not. It also compares unequal groups. We don't get to equalize our groups. We have to collect data from the outside world, and we can't make, in most cases, we can't make random assignment in post facto design. There are times during surveys where we can do random assignment by switching the order and so forth, but it's much harder to do than when we have a lab. So regression analysis compares unequal groups. That doesn't mean that the analysis is something that isn't worthy. It's worthy to have this information, and it's easy to make conclusions based on the evidence, but the assumption of causation is much less valid in regression. It has to be justified. It's much easier to justify it with experimental design than it is with regression. Now, ordinary least squares of regression, though, has advantages that experimental design does not. First, correlation is the basis of the analysis results. So it is just exactly like experimental design on that. Independent variable moves, dependent variable moves. We measure it, do a t-test to see if that difference is significant, and then we can conclude on whether the null hypothesis should be rejected or not rejected. The analysis looks to see if changes in the IV result in changes in the DV, just like experimental design. So that's an advantage. Correlational data is there just like it is in experimental design. Also, there's no need to assume that all the subjects will be impacted equally by the independent variable. With regression analysis, we can assume unequal impact, and we can embed that into the model to see if these effects actually exist. This is something you need to remember on your future assignments. When you see a regression is able to show you that, hey, among these people, the effect was very strong. Among these other people, the effect didn't exist. We can see that with regression analysis. We can't see that with experimental design. Also, external validity is far greater because most of the data is actually collected from the real world. We are looking at the real world, so we can say, oh, this is what actually happens in the real world. When we do it in the lab, we're not sure if people will react the same in the lab as they will in the real world. But with external validity, when it comes to external validity, regression analysis is very good. And with regression analysis, IVs cannot be manipulated as they are in experimental design, but it means we can use those variables like gender and race and age, independent variables that we can't move. We can't change somebody's age. So when we have those independent variables, we can study to see if people in those categories react differently than people not in those categories. That's a big advantage in regression. So the IVs can't be manipulated, but they can, if we have IVs that can't be ethically used, like we can't force people to smoke, we can't manipulate certain variables, we can still use those in regression analysis. So that's a big advantage of post-facto design. Experimental design and post-facto design have a major place in social sciences and nonprofit management, public administration, sociology, government, psychology. They have major places. We should value both because both designs give us valuable information that we couldn't get if the other design did not exist. That's this presentation on hypothesis testing with experimental design and post-facto design. I hope this helps you with your test and helps you with your assignment. I think this will definitely help you with both. Remember that this is supplementary. This is not where the test questions come from. Test questions come from your reading. But I don't believe there's any contradiction, and this is only designed to help you do better on both of those assignments. So good luck going forward, and thank you for your time.